The correct answer here is D. The correlation coefficient is going to be somewhere around negative 0.5. How do you know that? Well, a lot of these choices are obviously incorrect, so -1 and +1, clearly all the dots don't lie on the line. The correlation is also not 0 because you can see that the line has some slope. And E would be incorrect because you can see that the line has some amount of modest correlation here. It's certainly not strong, but it's negative because our slope is negative, and it's 0.5 here. As the line is going down, it's 0.5 because it's kind of a modest correlation. The correct answer here is B. A covariance of 0 indicates no correlation. A covariance is a standardized covariance, not correlation coefficient. That's why A is incorrect. A correlation C is incorrect because a correlation coefficient with a highly significant p-value does not necessarily indicate a strong correlation in terms of the magnitude of the correlation. You could have an R of 0.001 that was highly statistically significant if your sample size was big enough. And D is incorrect because it's the correlation coefficient that's unitless. The covariance has units. So in this question, we're given an outcome of cholesterol. That's a linear regression equation, which has an intercept of 150, plus 2 times our age past 40. 2 is our slope here. Notice the units are in age past 40, so you have to be careful about that. If we wanted to get the predicted cholesterol for a 60-year-old, his or her age past 40 is only 20, so we would plug 20 into the model here. So our yi hat, our predicted value for this person, would be 150 plus 2 times 20, which is equal to 190. In this question, you have to pick out the regression equation from the output like I did in some of the videos. So what is our model here? Our model is that our outcome, our optimism score, is equal to the intercept is 77.97. I'm finding that right here. Plus our beta is 0.276. And our exercise is in units of hours per week. So which of the following is true? So A is actually correct because it says a person who exercises 0 hours per week is predicted to have an optimism score of 77.97. Well, that's indeed true. You can just plug in 0 here. This is actually going to go out of the model, so that's what an intercept means. The intercept is the value for which you get at an exercise level if the x variable is 0. That's your where it crosses the y-axis. So 77.97, that would be the correct answer here. B is incorrect because exercise is not significantly related to optimism. Our p-value came out to be 0.12. C is incorrect because every additional hour of weekly exercise was associated with a 0.276 increase in optimism, not decrease. Otherwise, it would have a negative sign. And D is incorrect because that is the intercept. It's misconstruing the intercept. The intercept is 77.9, not the slope. So we're given here that we have a regression equation. Cholesterol is equal to 150 is the intercept, 2 is the slope. Our units here are age past 40. So if we have a 60-year-old, then we would say his age past 40 is 20, so we'd plug 20 into the model. That would give him a predicted value, a yi hat, of 190. This is asking for the residual. So what's his observed, his actual value? The residual is your observed value minus your predicted value. His observed value, his actual value is 250. His predicted value is 190. So he would have a residual of positive 60, which is A. In this question, we're told that we've run a model with DSST score as our outcome variable, and our first model contains vitamin D and age as predictors. The beta for vitamin D we're given is 0.30, and we're given the 95% confidence interval, 0.2 to 0.4, which means we know that it's statistically significant at the 0.05 level. We then run another model in which we add an additional predictor into the model. We add exercise. The new beta for vitamin D turns out to be 0.15, and the confidence interval goes from 0.05 to 0.25. So by adding exercise to the model, we drastically reduced the size of the beta coefficient, the slope between vitamin D and DSST. It was reduced by 50%. That's an indication that we have confounding. Exercise is a confounder of the relationship between vitamin D and DSST score. So A is correct here. If you picked B, you got misled by the p-values here. So we do have a statistically significant beta in both cases. That is, the relationship with vitamin D doesn't completely disappear when we adjust for exercise, but we don't look at the p-values for judging confounding. We look at the magnitude of the slope of the beta coefficients. In this question, we're given the mean blood pressure of 3 groups. So for the high exercise group, it was 120. For the medium exercise group, it was 125. And for the low exercise group, it was 135. If I fit a linear regression model where I don't have anything else in the model other than this categorical predictor, what's the resulting linear regression equation going to look like? Well, my outcome here is systolic blood pressure. I have to choose something to be my reference group. I'm going to be dummy coding this categorical predictor. Well, which one am I going to choose to be the reference group? Well, you could choose any of these to be the reference group, but you're limited in your choices in the multiple choice question. So you can see that in most of them, I picked 120, the lowest blood pressure group, the high exercise group, to be my reference group. So I made this one my reference group because it happened to have the lowest blood pressure. So the intercept becomes the mean for the reference group. Then I'm going to have 2 dummy-coded predictors in my model. I'm going to have a dummy-coded predictor for if you're in the medium exercise group versus anybody else. Their mean is 5 points higher than the reference group. So that beta is going to have a value of 5. And we're going to be multiplying that times 1 if you're a medium exerciser. That's how we dummy code. Then we're going to have a dummy-coded predictor in the model for the low exercise group. The difference between the low exercise group and the high exercise group in the mean blood pressure was 15, so they get an additional 15 for their blood pressure. We're going to be multiplying that by 1 if you're in the low group. Everybody else will get a 0 for that dummy-coded variable. So the correct answer here would be D, because only D represents the correct equation. In this next question, we're given unadjusted means for 3 groups, the high, medium, and low exercise groups for blood pressure. They were 120, 125, and 135. So the lowest exercising people have higher blood pressure. We then adjusted those data for age. The adjusted estimates for the mean then become 115, 125, and 140. So what we notice is that when you adjust for age, the disparity between the 3 groups actually increases. It looks like there's an even bigger difference between especially the high and low exercise groups. So what does that tell us about the relationship here with age? In general, I've told you here that blood pressure will increase with age. So if blood pressure is increasing with age, and adjusting for age makes our differences between the groups look even bigger, then what we can conclude is that the high exercise group actually was older on average than the low exercise group. When we adjusted for age, there's actually a bigger difference here. In other words, if in the original sample, when we didn't adjust for age, we saw a 15-point difference between the highest and the lowest exercise groups. However, when we adjusted for age, that went up to a 25-point difference. So what must be happening here is that we happen to have some older people in the high exercise group, some younger people in the low exercise group. And once we adjust for age, we're revealing that the difference in blood pressure between the exercises is even bigger than we saw when we hadn't adjusted for age. In this question, we're told that we've got a study where we've got a group of just 14 women, a subgroup. We've run a linear regression model on just those 14 women, and we get this miraculous R squared of 99%. Well, if it looks too good to be true, it is. Once you stuff too many predictors in the model, especially with a small sample size like this, you're at high risk of overfitting. That high R squared value reflects an overfit model. So C is correct here. The model suffers from overfitting.